density class on Monday. I wonder what that is about. All right, so we are on a fast track to the end of semester. Do you realize that 2 weeks from now, classes are over? So that's Monday. So there's a lot to actually complete before. One thing that is a big thing that will be posted today is computational project. So you typically have 2 weeks to complete. So in terms of work, we expect that it's sort of like twice the work you normally need for a homework to complete. And it's a teamwork. So really it's 4 times, but hopefully both parts of the team are doing their part. Now, we normally like 2 and maybe 3 in a couple of occasions. So mostly 2 people per computational project. And 3 just in a couple of cases where we couldn't pair the people correctly. So, this is up to you. Do you know who you would do the project with? Or do I need to assign?
Okay. How many people per project?
2. Okay? And in 1 or 2 extra cases, I'm going to do 3, but basically 2. So you know who you would do it with? So then I'm going to leave it to you. You're just going to report to us. Okay, but start thinking now or talking right now who are you going to do that project with. So what is a team? Okay, team has to work together, and if one person does everything, that's not going to go well. It might go well because if that one person is motivated, they will complete everything anyway. Okay. But it's going to sour your personal relationship for a long time afterwards. So make sure that you do your contribution. And often, it means actually being transparent about what your strength is, which is difficult. It's hard to admit. Say, I'm good at this, but I'm not good at that and that. How do we go about it? So if you're part of the team, transparency and being honest is the key starting point, and it's the hardest part. Right? You're not on your own, and the consequences of you not contributing are not your own only. Okay? So you have to have a little bit more responsibility. Yeah? Dancing doesn't work if one of the people are not carrying their weight. Nobody dances like this. Okay? It has to be proper frame, proper transfer of weight, because if there is no communication, one of these hands is falling down, there's no dancing, okay? Not coupled up anyway, okay? So, you gotta dance, okay? So, if you immediately know, look, I'm so stressed out in these 2 other courses that it's gonna be hard for me to focus on this computational project, then say so immediately, and then put yourself on a schedule to meet regularly and debrief you regularly and keep the project moving. Okay? And that's basically one of the key things that you will need once you start working wherever it is that you start working. You're not going to work alone. In rare industries, especially not in petroleum industry. Petroleum draws from different types of expertise, and you're going to have to translate, what it is the geologist is saying to you, okay? So, team will have varied disciplines, and communication, good communication is the key. So, knowing that, again, know who you're going to couple up with, start talking to them, be okay if they don't want to work with you, okay? Or they already signed up with working with somebody else. No hard feelings there, be adult about it, okay? For a team to work, both people have to want to be in the team. And communication, often, even if you're communicating that you didn't do anything, communicate that. All right. And that way, you're more likely to succeed. All right. So computational project will be posted. So you will just report to us who the other person of the team is. If you do have trouble finding a teammate, let me know, and then 3 people will let me, or 3 or 4 people will let me know, and then I can then help with that. Okay? So That's computational project. Grading, as projected, we did not finish for today, but grading will be finished by sometime tomorrow, and we will then place the tests in your mailboxes so you can get them before. So apologies for that, but this weekend.
Are you going to post the grades on campus too?
Yes,
okay.
yes. All right, and I'll post the solution. All right, let's just briefly wrap up Lecture 6. And that is just like one piece of information that I hoped to finish last time, but I went a little slower than usual, and that is condition number of a matrix and matrix norms. Okay? So just like we measured vectors and wanted to compare vectors, we also measure matrices. Now it is not clear why would you want to measure matrix and why would you compare two matrices. With vectors we kind of know. If it's velocities, well, we need to measure speed to actually compare two velocities, right? We need that single number to compare things. With matrices it might not be as transparent. How would you measure them? And actually they are measured through their performance in solving linear systems. So technically, norm of a matrix, and there's a way to get that norm that I'm going to define in a moment. Norm of a matrix as well as the norm of its inverse together give me something that we call condition number. And condition number tells me how is this matrix going to perform if it's part of a linear system and we are solving a linear system better. That's the biggest and most important actually measure of how matrices do and how do we compare to matrices, how they actually perform in linear systems. It's not the only one, but it's one of the most important in applications. Okay? So let's actually figure out, so let's remind ourselves with vectors, we had L1, L2, and L infinity norm. Okay? And with matrices, we're going to have actually something similar, and we will add one more Frobenius. Out of those, L1, L infinity, and from Frobenius norm are easy to compute. L2, not so much. So Frobenius norm, it looks like it's L2 norm, but it's strictly speaking not L2 norm because of the mathematical definition of the norm. So basically take squares of all of the values in the matrix, sum them up, take a square root of that. End of the story. That's Frobenius norm. Now, if I have the way we actually define matrix norms is in the following way. I take all of the vectors in certain norm that are of norm 1. They're technically, if you think about them in a three-dimensional space, they're part of a sphere with radius 1. Okay? In a coordinate system, right? So those vectors, they end on a sphere. They point to a point on a sphere. And then I'm looking at a times x for those vectors. And where does this linear transformation send those vectors? So if I'm thinking about the simple matrix like 2, 2, 2 on diagonal, 0 everywhere else, that's going to expand every vector twice in all directions. So all of those from sphere 1 will be sent to sphere 2, or radius 2. Yes? Can everybody visualize that? Okay. So for all of those sphere, I look at where did the linear transformation map them into, and I take the maximum norm of that. Now in this case of diagonal matrix, that was simple. But in case of a regular matrix, figuring out where are all of those going to end up is not so easy. And especially for 2 norm, it's not so easy to compute by hand. Okay? The 2 that are actually easy to compute by hand are 1 and infinity norms. So first things first, I need, so basically I have my A, and I'm going to go and look at A as an assembly of 3 columns. Okay? For each of those columns, they're vectors. I'm going to compute L1 norm of those columns and look at the maximum of them. That's it. Okay? So our L1 norm was summing up absolute values. Right? So for, let's say, for this matrix A, what would be this L1 norm? Can you take a piece of paper? So I have columns. First column is 1, 4, and 3. Second column is 2, 5, 2. And third column is 3, 6, 2. Yes, so what is the L1 norm of the first column? 8, 9, 11. What's the maximum of that? No, not sum. 11. Okay? So norm 1 of the first column is 1 plus 4 plus 3. That's 8. Norm 1 of the second column is 2 plus 5 plus 2. Everybody sees that? That's 9. Norm 1 of the third column is 3 plus 6 plus 2. It's absolute values of these. I just summed them up. So this is 11. So maximum among 8, 9, and 11 is 11. Yes? So I go column by column, find norm ones of those columns. Okay? Now for infinity norm, and this is something that I have to actually always have written, and I'm going to always mix up. For infinity norm, we do the same, but we just go row by row. So good luck remembering which one is column, which one is row. That's the first thing you're going to put in your cheat sheet for final. Okay? Is that this does the same, it just goes row by row. So what is 1 absolute value of 1 plus absolute value of 2 plus absolute value of 3? That's 6. So that's my norm 1 of this row. Okay? Then what is absolute values of these numbers here added up? 15 and 7. So maximum is 15. Okay? So we can immediately see that norm 1 versus norm infinity will give me ever so slightly different number. It's not a big deal that they're different. Really, on the order of magnitude is just fine for any kind of important behavior of those numbers. Okay? And that's similar to actually norms of vectors. Okay? All of the norms are actually ultimately related in the sense that if one of them is bounded by a number, the other one is not bounded by a number times some constant. So it's not a huge deal. All right. Now, what is the condition number? Condition number takes the norm of matrix A times the norm of matrix A inverse and multiplies them. And that norm could be in any of the norms that I named. So in this case, you can again slightly get a slightly different answer, so you can actually figure out what is the norm in any of these for inverse, and then multiply them together. For this matrix, I believe this was the norm 2 actually, because these numbers are nothing that I computed on the previous page. Okay? So basically, you will get something like 60. 60 is not a big deal. What a big deal is when solving systems is something like 1,000,000. Okay? Those systems are not well conditioned. And what that actually means, it means that actually A inverse is almost, it's hard to find. And because of that, numerically, I'm going to pile up a lot of error when computing the solution to the system. That essentially, that's what it means. Now, the way it's mathematically expressed, okay, is that if you have ever so slightly change in coefficients of A, technically if I'm solving AX is equal to B, And then I just slightly change coefficients of A. Okay? I don't expect a large change in the solution, do I? However, if my solution actually changes by a large number, that's what I mean by an ill-conditioned system. Now, what does it mean in engineering? That's mathematically, and that's what's mathematically expressed here. So if I have a very large number here as a condition number, okay? And I change A slightly, okay? Then large number times a small number, this is still going to be large, and basically allows for a large change in a solution, even though I changed matrix only slightly. Okay? And that's why a large condition number is not good. Now that's mathematics. And kind of it makes sense that my solution shouldn't change in some ideal world by a lot. What does it mean in engineering sense or scientific sense? If you remember how we composed systems, and if you are solving the homework that has formation of the, typically my A is populated by things, coefficients that are telling me something about my physical system. And in this pipe network, it would be, for instance, if I'm solving for concentrations within these fluxes, which are ultimately literally bounded by like how big is my pipe. Okay? So as an engineer, if I put a pipe here that has radius 3 centimeters, okay? So this one has 3 centimeters, and now suddenly I go on my next iteration and change it to 3.1. I don't want the whole stability of this flow in the system to change a lot, do I? So that's essentially, I expect, and even if I just made a mistake and produced a pipe that is 3.03 centimeters as opposed to 3 centimeters in radius, it shouldn't change my ultimate solution a lot. Right? So that's essentially what this natural expectation of systems to kind of behave similarly if they have similar coefficients. Okay? Because these coefficients ultimately come from some sort of physical restrictions in my system. And that B, okay, just a moment. Now, there you go. Bye-bye. All right. Apologies. So that's essentially what condition number tells me. So let's actually see how bad it can be. So one of the systems like that is right here. So do you have your Python open? If not, open it up. I'm going to actually do a new one. So I'm going to literally type in my favorite matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. So import NumPy as NP. Three, 4, 5, 6, and 7, 8, 9. And then I'm going to use B as 108 and 9. No, 8 and 10. Doesn't really matter what I use B as, but it's also going to be NP. And you can use your solver or NumPy's solve. The method of solution doesn't really matter that much right now. So if I get a solution, whoops, what did I do?
You're missing brackets.
Oh, look at that. And I need to print. All right. So here's the solution. The moment you get plus something to the 10 of 17, that's a flag right there. Now, let's actually repeat the same, and I'm just going to create a slight variant of this matrix. I'm going to call it C. So I'm just literally going to change one coefficient to 9.1. This 9, 9.1. I changed it by 0.1 over 9, small fraction, right, over 9. So it didn't change it by a lot. And let's see what change does it make. So I'm going to create a new solution Y that is the same thing, but I'm using C instead of A. And let's see what is the... See how much my solution changed? And condition number is actually indication of that. So if I actually go and compute condition number of A, you can use linealg norm. Just like you used it for vectors, you can actually use it for matrices as well. So we're just going to quickly compute A norm 1 times, and we need A inverse. What's the inverse? Does anybody know in the NumPy? It's NP dot. Somebody said NV dot. Good start. Linealg as well. You know, try inverse or INV, huh? INV. You can also always Google it, but basically I'm going to compute norm of A and norm of inverse of A, and I choose one norm. Doesn't really matter. And you can see that the condition number is really large. So we're not going to elaborate on it further, but just know that if you were in the business of solving linear systems a lot, and basically, as I mentioned, solving differential equations means solving linear systems a lot. If the systems you result in, if you kind of get these constantly off solutions, and you don't know why, maybe it's because of the matrix that you're using is not well conditioned, and then you have to, there are solutions that are called preconditioning. Then you have to work with it a little further to get a satisfactory result. Okay. So it's something important if you actually end up solving these systems. Okay. That is it for linear systems. This is our final sort of comment. And we are going to actually now switch to a new topic. And that is curve fitting. Curve fitting, again, is just an application of linear systems. But it's going to be something that you do a lot. So let's get to it. A lot of times we have data, and we don't always have functional relationships that data obeys. So we are kind of looking for those functional relationships. So I could just have a bunch of points up there, and then I'm looking for some, we call that a trend. I'm looking for a function that describes, and I typically plot one variable versus another. And then I have two options. One is to attempt to draw a function through all of those points precisely. And that's what this interpolation tries to do. If data is messy, not a good option. However, interpolation is still very important theoretically if I want to, for instance, integrate something. And we didn't actually have a topic of interpolation, which is just basically balancing the time in this semester. Now, sometimes I might just want to kind of fit a trend through the data. This is also understanding the data is not perfect. So if I try to fit it perfectly, I'm fitting errors perfectly as well. Okay? And that can be a problem. So that type of fitting is called regression or curve fitting. So it's more looking for a trend without necessarily trying to go through every point precisely. So there is a major difference between interpolation and actual curve fitting. But I also have to know what is the type of the function I'm trying to fit. In this case, I chose a line. It doesn't have to be a line. So one important part about curve fitting is knowing what it is that you want to fit, and we will see why in a second. Okay? So here's an example for petroleum engineering. Does anybody know what capillary pressure is? When I have two fluids, okay, then one displacing the other, there's typically a capillary forces between at the interface of those two fluids, right? And so if I think about a capillary and I have sort of like an interface of one fluid trying to move in, right? In porous media, that's very important because our capillaries are very small. So anybody has a bottle? See-through bottle? May I borrow it? So here, I do not see much of the curved interface between water and air. However, as the radius of this capillary goes down, and in this case it's a few centimeters across, in a porous medium, it can be 20 microns across, if you're lucky. In shale, it's 20 nanometers across. Okay, that's called unlucky. So capillary forces, they scale 1 over radius. So the smaller the radius, they're larger. Okay, and that's what's often trapping one of the fluids in a porous medium. So to push in, okay, and displace, we want to get the oil out, right? So to displace that, I gotta actually push in water, or I could push in gas, right? Either way, so we described that, so there's a capillary pressure between two fluids, there's a jump in pressure at the interface, and that jump is larger the smaller my radius of my cross-section is. Okay? So we often describe that process with plot of capillary pressure versus saturation of the wetting phase inside my porous medium. Okay? And the way we measure that, we measure it in the lab. We have a core, we have pressures in one tank of fluid versus the other. Whoever is displacing whom, doesn't matter, right? And I take the differences between those two at the endpoints. And I can measure saturation by simply weighing my core, okay, and calibrating it. So essentially, I will get these points, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so forth, right? And I want, for reservoir simulation, I need that in a functional form. So I need to fit those points so that I can throw them into a simulator. Okay? And that's actually here done with so-called Van Genuchten model. It doesn't matter what the model is right now. Okay? So that's one application where I might want to say I have two things. Now, this doesn't mean that capillary pressure is only a function of this saturation. That's just how we're modeling. Okay? So it's often taken because that's just a simplification that works, right? So often actually for a different set of settings, so this is drainage. My non-wetting fluid is displacing the wetting one. On imbibition, I'm going to go down, and I'm going to have a slightly different relationship. And we kind of tend to, so it's not the unique, capillary pressure is not the unique expression of saturation, but it's modeled that way, and that's important to think about. Okay? We choose to model it that way. Second example where we are often trying to predict is permeability versus porosity.
Now you haven't had petrophysics. I don't think anybody has had petrophysics. These are two will come up in petrophysics. But you have had introduction to petroleum engineering, right? You must have mentioned permeability and porosity, even if you don't remember it. Remember it. Very important two things, okay? Porosity basically means what is my storage in porous medium. Okay? How much can I fit into the rock? Volumetric. It's a volumetric fraction. Permeability is how fast can I get it out. Two very important things, actually two only things you need to know in petroleum engineering. How much is down there and how fast can you get it out. Okay? So these are very important in describing reservoirs. So often what we have is data. They're not, permeability is not a simple function of porosity, though we would like it to be. Okay? So what we often do is we get a whole lot of data. Look at these, all of these points around, right? And then we are trying to fit a trend to it. And in this case, a straight line would not do. Actually, in either of these cases, the straight line would do a terrible job. Right? So we are trying to find a function that is describing the data, and then that's the function that I can actually use in my predictions. So do this in the lab, and then it's for that kind of reservoir, you do it for experimental well, for instance, and then you work with that for all of the wells in that reservoir that are not very far. Okay? All right. So data, but data comes in a lot of forms, and if anybody has heard of data analytics these days, okay, it's curve fitting. It's glorified curve fitting, trying to learn from data. What is data telling you without you actually having physical explanations of the relationships? Okay? All right. So let's do the simplest one, is the straight line. So how do we actually go about it? So here's what we do. We have data. So here are the data points. And let's say that I'm trying to fit a straight line through n points. Okay? Everybody sees the points? This is my n points. These n points, all of them are, so this is x1, y1, x2, y2, x3, y3, and so forth. Yes? Excellent. So these are my x's and y's. I have two vectors, one with x's and one with y's. This is how we're going to implement it in Python. Right? So each point is described by a corresponding x and corresponding y in those two arrays. Great. So now I'm trying to figure out the relationship between every x and every y that is linear. Therefore, that relationship looks like y equals to a0 some coefficient plus a1 times x. Yes? Slope, intercept of a line. Slope, intercept is very small here. Well, it's not actually. This starts at 1, so it's 1.1 or something. Yes? And then there's some error, because I'm not going to do this perfectly. And what we're going to try to do is simply minimize that error for the data given. So what is the error? Whoops. In this particular line, okay, the error, for instance, right here for this point, if I'm predicting y with this line, y would be right here, correct? But my point is actually here. So this is my difference. That's the error. Yes? Here, it's a little larger. Not a little, it's larger. Here, it's not larger, but it seems to be opposite sign. Okay? So this is my prediction. What this line would describe, this is the y as the line sees it. Yes? A0 plus A1x. So if this is my x right here, this would be y as this line is seeing it, but the actual y is a little above or a little below. There's a difference between the two, and that's the error. So question is, what is the best way to sum up all of the errors at the individual points and somehow minimize them? Okay? I'm not going to be able to do the perfect job at every point. But how I'm going to kind of average it out and do a good job given the points? And that's our question. Now, the problem of this plus-minus business, okay, is that sometimes if I allow these errors to be both positive and negative, I might not get a unique solution. So, for instance, if the points are canceling each other out, right, then in this case, this and this, so if I have these 2 points, a straight line goes through them. It's great. But basically, if I allow, and error is 0 here and 0 here, correct? Now, if I kind of flip a mirror of that, and I allow, this is my, if this is my prediction, then this error is positive, and this one is negative, and they would cancel each other out. So technically, if I allow positive and negative errors, then both this, when I sum up those errors, this and this give me the same summation of the errors, which is kind of a bad idea. So I don't want to allow positive and negative errors at the same time, because they might cancel each other out and I might not get a good fit or unique fit in this case. So I don't want to just plain sum up those errors. I'm calling them EI here. And my error is really, this is my data point minus prediction, okay, by a line here. So I don't want to just go and sum them up, okay? Now, if I throw in an absolute value, I might have issues as well. Instead of graphically, I'm going to explain it the following way. So if I have 4 points, well, if I have 4 points like here, okay, and then if I throw a line this way, I'm perfectly fitting these 2 points, okay? And I have an error fitting these 2 points, okay? But then this line and this line would have the same error. And I would possibly, like in this case, to sort of go in between them and have a unique solution in between, right? And not perfectly fit 2 and not the other 2 and have a mirror problem. So just absolute values, not so good either. And then one thing that I could do is just square them up. That would give me a positive value. And I also don't want to do I could also minimize the maximum distance, but then one outlier would kind of draw the line too far away. And I don't want that either. Okay. So what people have agreed upon is that, okay, just doing the squares of this error between the measured and the model. And then square, there's a missing square up there, I apologize. There should be a square here, square. That seems to give a good behavior. Nothing's ever perfect. If you have too many outliers or too many errors in data, you can't overcome that always. Okay? But this seems to behave the best. Okay? And will not give undue, and will give a unique, typically a unique solution. Okay, so let's go with the squares. Is everybody okay? How are we analyzing errors? And why are we choosing squares? This is what's called, so-called, we're going to minimize some of these squares of what's called a residual between a measured and a model value. And that's called least squares fit. Okay? All right, so what do we do? This is what I'm trying to minimize. This is a classical problem of optimization, and you will hear optimization a lot. Optimization has so-called an objective function that I'm trying to minimize. In this case, our objective is to minimize some of these residuals. Yes? So I'm just like translating what you thought you understood into words that you don't. So basically, objective function is this sum of the residuals, and your objective is to minimize that sum of the residuals, okay? That's always a problem when you're trying to optimize the system. You're trying to maximize something, maximize profit, for instance, or minimize error. That pretty much sums it up. What you're trying to optimize in life in general. Just define your profit or define your error. All right? So, okay, we have our objective function. So this is some of these errors. And I'm going to try to minimize it. What are the unknowns in this SR? I know every yi, right? I know every xi. Yes, that's my data coming in. Those are the things I know. I might have 1,000 of them, but I know them. What don't I know?
A1, coefficient.
A0 coefficients, A0 and A1. So this is actually true regardless of the model we pick. Here we picked a linear model and it has two coefficients, A0, A1. In some other case, you're going to pick a slightly different model. And it's going to look slightly different, but it's going to have a certain number of coefficients. It's going to be a function that has a number of coefficients. Not to pull out frustration from the exam, but that Reynolds number was unknown in the equation that I posed for friction, finding friction factor. Okay? So you will have certain parameter you depend on, and in this case, these are A0 and A1. Okay, excellent. So this is what I don't know. Well, so this SR is a function of A0 and A1. Looks complicated, but that's all it is. Given my data, xi and yi. Yes? It's a function of two variables. And I'm looking for those variables. So when I have a function of one variable, f of x, what is true for a minimum? Derivative is 0, right? Remember that from calculus? First thing you need to know from calculus is Taylor formula. Second thing, definition of minimum, maximum, or saddle point. So f prime of x has to be 0. Well, if I have multiple variables, same thing has to be true. It's just that I have to look at the partial derivatives. So my gradient, remember the gradient, definition of a gradient? It's partial derivatives with respect to all the variables that I might have in my coordinate system. So basically my gradient as a vector has to be 0, even for functions that depend on multiple variables. So this f prime of x is equal to 0, it has to be just generalized into multiple variable, multivariate calculus, and that's your math 427J, the lovely one, right? So in that lovely one, you had multivariate calculus, and actually the same is true for minima and maxima and saddle points of functions that depend on multiple variables. The entire gradient, so for every partial derivative, has to be 0 as well. It's a direct generalization. It's not necessarily easy to find, but it's a direct generalization. Excellent. So basically I have two variables, A0 and A1. And my partial derivative with respect to A0 of SR has to be equal to 0. Okay then, well, we do a partial derivative of this with respect to A0. There's a square here, so it's 2 times this entire, you can just work with the entire sum. You're just working with all of them individually. So it's 2 times yi minus, and then there is a function of A0 in here. Its derivative is -1. Yes? That's how minus shows up. So chain rule. That's square of a function of A0. Yes? And sum of them. Is everybody comfortable that this is my derivative with respect to A0? Okay. That has to be equal to 0. Same thing for A1. Okay. It's just that now I have not just -1, but I also have xi multiplying A1, and that xi is a number, some number comes with my data, but it's a number. So this is my partial derivative. And sum goes over every however many data points I have. Might be an ugly sum, but it's just still relatively straightforward. Excellent. So now I just have to figure out, clean this up. How do we solve? This seems to be a linear equation in A0 and A1, and another linear equation in A0 and A1. That's A1. That's the good news. So you have two equations in two unknowns, and both are linear. System of linear equations. Whenever you get a system of linear equations in the unknowns you're looking for, smile. That's the good news. They might be complex, but we have, or there might be a lot of them, but we have a lot of ways to deal with systems of linear equations. Non-linears that we didn't even touch in this one. Okay? All right, excellent. So now I just have to clean it up, and yes, it looks like a little complicated, but what do we have? Every time I'm setting up a system of equations, whatever I don't know is on the left, whatever I know is on the right for systems of linear equations. So basically, this I know, so it has to go on the right. I have something multiplying A0, okay? And basically something multiplying xi. So I have sum of yi's. I can basically just divide by -2, it doesn't matter. So I have sum of yi's minus sum of A0's minus sum of A1 xi's. So I seem to have n of these, right? So it's n times A0 plus sum of all of the xi's times A1, when I take A1 out, is equal to sum of yi's. Is everybody comfortable with this transformation? N times A0 plus some number, which is sum of all of my data, times A1, is equal to sum of yi. Yes? Second one, similar transformation. I'm going to have sum of xi's, sum of xi squares, and sum of xi yi. This goes over, this sum goes over all of the data that I have. So this looks scary because I have these sums in there, but it's really a 2-by-2 system. Yes?
So xi is down?
Yes, that's my data. X's and Y's of my data. That's just every point has an X coordinate, every point has a Y coordinate.
Okay.
I put X coordinates in one vector, Y coordinates. I'm sorry that wasn't clear, but that's what we
So
started
you
with.
have to use it to solve it?
Correct. So basically, all I need is to set up the system, okay, and sum up. We know how to do that sum, right? We did that at the beginning of the course. All of these sums are easy to do.
But you have to do that with the linear system solve for the sums.
You move and find these coefficients. This is your matrix A11, A12, A21, A22. And this is your B1, B2. And you solve with this small system AX is equal to B. Which is your X's are A0 and A1. No, one. And that's all we have left. That's it. You need to do 4 for your computer. And that's what you're going to call okay? Happy Thanksgiving!
Quick question. I'm a little worried about the project because I have to leave for meet on Monday afternoon, next Monday.
And then?
And I get back Monday morning.
Oh Lord. Okay.
And I can't work on it while I'm there.
Yeah, I get
Just
that.
because we have session in the morning,
you're
math,
me?
session in the night.
You've lost the week of lost. Let me just stop the video.